We went to put it all the way down. Yeah. 2, 3. Okay.
Alright, welcome to the afternoon session. We have 3 more talks today, and the first one will be by Andreas Kupper for what I presume will be about debris of floating clusters.
Correct. So, I was working I'm currently based at Columbia University, which is in beautiful New York City. Stuck here, I put this up for stuck home. Water adventure is stuck. This is Central Park, and Columbia University is here in this northwest corner of the city park. So it's very beautiful. Come visit us. Sarah's also there. So tidal debris of globular clusters, why should we care? Since the 70s and this woman here, Vera Rubin, we know that spiral galaxies rotate faster than they should. If we just add up all the baryonic matter, looking at the rotation curves to determine that there must be a significant fraction of some dark matter or some modified gravity or whatever. Unfortunately, like for our own galaxy, we cannot easily produce a rotation curve. Several attempts have been published. This is from Andreas, recent paper collecting H1 data, CO data, and masers all over the galactic disk, and try to produce a rotation curve like we can so easily do for external galaxies. So if you try to model the galactic potential of our Milky Way and try to reproduce this rotation curve, you already see that you will need some form of dark component even within the quite limited data for the Milky Way, which is out to 10 kiloparsec. In this model here from Andreas, they infer that, of course, this is a vast extrapolation here, but within this radius of 100 kiloparsec, the dark component, if you assume it's an NFW profile, dark component, has to have like 1.7 times 10 to the 12 solar masses, so it's the dominant part in mass of the galaxy. So what else do we know about dark matter in our galaxy? All we do know comes from cosmological simulations of spectral formation, like this one here, so we like TR2 simulation from the Demand from Zurich. Dark matter only simulation of a Milky Way sized dark matter halo. You see here, the top here is the scale, so this is 40 kiloparsecs, pretty much the inner halo of our galaxy. This is more or less what the dark matter distribution in our galaxy should look like. And if you measure the shape of such a halo, what you typically get is something triaxial. And what you also can see here is substructure, like very significant substructure orbiting within such a halo. But unfortunately, it's all dark, so we don't see it. So tidal debris can help us to see what we don't see, to measure the shape of this dark halo, and that's what we're trying out now. We look at SDSS, very deep survey in the northern sky and also the southern sky. This is looking into the halo of the galaxy. And what you can see here, there's substructure, stellar substructure, very famous Sagittarius stream, which is a whole galaxy stream which wraps around the whole galaxy. And what you also see is GD1 stream is a very thin stream, most probably from a dissolved globular cluster, the remnant. It's also a more nearby orphan stream. And I'm going to talk mostly about this one here, Palo 5 stream. It's like a famous globular cluster stream. But just this morning, there was the discovery announced by Carl Gribmeier. He brings out every few weeks or so he discovers new streams. Just in his data set, it's just So in principle, everywhere you look with a deep survey, a wide field survey, and you apply some matched color filter, you always find some sort of stream. So our halo is really full of streams. It's a bit hard to see here, but apparently this is the structure he claims to find. Very long, and another one running almost parallel to that. Not much information about that. Just this morning. So it's a very active field right now because all these surveys are coming up and there are more and more streams being discovered. But the first stream that was discovered was the Sagittarius stream. And this has been modeled excessively. The last and maybe best approach so far was from Law and David Law and ISIMA. This is their best fit model. So what they do is they construct a galaxy model, like a potential consisting of this and large in a halo, and then run an n-body model, a full n-body model of Sagittarius and look at the debris. This is the n-body model, and then they compare the debris to the observations. That's their best fit model. They modeled like 1,000 Sagittarius. And what they found is that best fit potential, this is like an illustration of the shape of the dark matter halo. I don't know why the colors, but apparently it's a very weird shape. So it's a triaxial halo like we expect, but it's like a disk, dark matter disk, but it's tilted 90 degrees to our baryonic galactic disk. It's a very weird configuration. So if you look at the literature, there have been many other people trying to model the Sagittarius stream. They found all kinds of, they found prolate halos, they found oblate halos, they found spherical halos. Recently there was Cambridge group modeling Sagittarius found spherical halo, which is very low mass. They claim to find that the missing satellite problem is not a problem because we just have a very low mass halo. It's a very controversial stream because it's very hot and broad, and observations are with large error bars. So that's why we want to go to globular cluster streams, because they are much colder, dynamically colder. They are very thin, and consequently you can measure distance easily because it's just one population, because it's a globular cluster. So, and the two most promising streams are Palomar 5 and CP466. This is from a recent paper from Lux. This is illustrating the galactic disk here, the sun is here, the sun is here, just showing where these streams are. So this is the Sagittarius stream here, and this is Palomar 5, and this is in the CP466, a very long structure. This is from the side, like this here, Palomar 5, in the CP466, and Sagittarius. You see, Sagittarius is very long, very long thick structure. So the question is how to model that. Yes.
People underestimate the orbit of the force it seems extremely high up. It's very difficult how to define in your environment.
That's what like very basic modeling suggests. And so far there's no kinematic data, so no radial velocity data. But in the project I was suggesting here, have some radial velocity data so we can try to look at possible orbits, where these radial orbits. So how to model streams? As I said, like Sagittarius was modeled for n-body simulations. There are different techniques how you can approach this problem. Direct n-body simulations, of course, would be the nicest approach. Just set up a cluster or a dwarf galaxy and you let it dissolve still consistently in some trial potential and look at the debris and compare it to observations and then say that the model is still advanced. But it's super slow. Simulations take at least a day, or depending on what kind of object you want to model, maybe a month or so. The simplest thing you can do is called orbit fitting. What you just do is you look at the debris and you try to find an orbit, just one line going through the debris. But this has been shown that it's a very low accuracy, it's very degenerate, and also produces biases, and we don't want biases. So what I'm suggesting is something in between here. It's the restricted free-body problem. So what we do is we assume that once stars have left the clusters, they don't interact among each other anymore. So we can treat the problem of cluster, debris star, and galaxy as a restricted free-body problem. It's called a Strickland problem, and I will show you how this goes in detail. So from Douglas' lecture, we've seen that very schematic what happens in a cluster. This is the cluster, and we're in a moving frame. We have these exponential surfaces here forming two holes through which stars can escape from the cluster into the tidal tails. And every star escapes through the Lagrange point, which is closer to the galactic center, speeds ahead, and the one and there are two, they stay behind and form the trading tail. So let me show you how this goes. And let's imagine you have a galaxy and there's a cluster going on a certain orbit. Now we'll show you an n-body simulation, full n-body simulation of cluster. Oh, no. Start now. Yeah, so cluster is very compact in the beginning, and we just go with the cluster around the galaxy, and you see slowly that on the right, this should be the leading tail here, this is the trading tail. And the stars, they funnel into the leading tail. And when we go around once, then the tails grow. You can also see here is that they form a substructure, which is very interesting. We can also use. I'm not going to talk about this here. And so it goes. So the longer the cluster revolves around the galaxy, the longer the tails get.
Where does it come from? Is it self-gravity?
No, this is epicyclic motion. So I can show you later a few slides how this goes. This, in principle, the motions along the stream are not linear lines here, but they are stars escape in epicycles around this, because there's small differences in angular momentum to the cluster. So there's always a relative motion between the cluster and the tail. And this is like a standing density wave in the tails. Okay. So there's a lot of information here. We're trying to make use of that. There's a lot of information in the location of the clumps, because it's proportional to the offset from the cluster to the Lagrange points where the stars escape. So in this distance here, there's a lot of information on the cluster and also on the gravitational potential, on the strength of the potential here. And as you will see now, for an eccentric orbit, we look at the same thing but on an eccentric orbit. It's the same game, stars escape, but then on top of that motion, out of the cluster, there's the motion of the whole system around the galaxy. So it goes into, so now it's going into pericenter, the thing is speeding up, it's stretched the whole system, and then going into apocenter, the whole system gets compressed, and it's getting stretched, getting compressed, and stretched. And what you can see is these overdensities form, and they also form these funky shapes here, which is very, very stable. So there's not just information. So in this distance from these overdensities from the cluster, there's information about the mass of the cluster, the strength of the gravitational field, and also about the orbital phase of the cluster of the galaxy. So, but as I said, these simulations take maybe a day, maybe a week. It's way too long to scan a huge parameter space of potential models.
So are the stars coming out of the cluster at a steady rate, or do you evaporate more stars when it's at very center?
That's a good question. So what I find, it depends, okay, crucially depends on how you define what's bound to the cluster and whatnot. If you define stars to be bound to the cluster when they're inside the instantaneous Jacobi radius, what I always see in my simulation is that the mass loss rate is just constant. Yeah. They may be in pericenter, the instantaneous Jacobi radius may be a bit smaller. And stars beyond this radius may be unbound for a time. But then they get recaptured as the star cluster, as the whole group moves into apocenter and the Jacobi radius grows. So they can be recaptured. And on average, you get a very linear mass loss rate.
Just while we're asking
Yeah.
questions. For the tails, where you see this pumping from epicyclic motion, does that suggest that there's a phase dependence on the stars as they're lost? Meaning the phase of the epicycle.
How do you mean that?
So, I mean, if they're pumping, so in my mind anyway, then there maybe would be some sort of relationship between the stars that came out, that were lost as they move around and they see this pumping from. Because they're in nearly the same epicyclic phase. Once they enter the galactic dimension versus the
Yeah, as I will show later, so these tracks of the stars within the tails are very complicated on eccentric orbit. They, especially if you have these freaky features here, they go like this. So it gets overdensed in this position where two tracks overlap. And the stars in one overdensity, they can be from very different like escape times. So there can be stars in here, for example, that were lost 2 orbits ago and 1 orbit ago. Yeah. So not really. It's hard to say. Okay, so coming back to the straight line modeling, very simplified modeling that it's a straight line, and the straight line just imagine you have some flow, some background fluid or a gas and so on, and you insert some object and you release test particles from a given point of this object, like for example, imagine this is the cluster, it's moving through the galaxy, and this is a branch point and we are just releasing test particles, and then we follow the airplane and these particles, how they evolve over time. And if we look at that picture compared to our observations of Alpha 5, and then we assess if it's a good model or not. And it turns out that with this very simplified description, you can reduce the shape of these streams. So this is now from the circular orbit model that I'll show you. The clusters here, the black dots are stars from the simulation, from the full n-body simulation. And the red ones here are like points from the streak line modeling. As you can see, you get this pattern here. You reproduce it very precisely. And also for the eccentric orbit, a bit more convincing here, you produce all these blank features to very high detail. And the big difference is that producing a streak line model may take like a second, whereas full n-body simulation takes a day.
So the streak line you're assuming zero velocity when it escapes?
Yeah, that's a tricky question. So we played around with this. Douglas and I, we published a paper on that. So you have different choices you can make, right? And we compared different choices. What we found is if you give the particles exactly the angular velocity of the cluster, then you end up with these streak lines I've just shown. If you give them the same space velocity, for example, the loops get too long, or you make them slower, and they get too short. So it seems like that on average, stars escaping from the cluster have the same angular velocity as the cluster. But of course, there's like in a real cluster, there would be a lot of spread around this.
Do you understand why?
Hmm?
Do you understand why?
What?
Why is it not speed and something?
No, it's a good question. I don't know. Okay, coming to Power 5. Now I want to apply this. Briefly, let me present Power 5. This is Power 5, beautiful cluster. You guys see it. Has a central density here, 1 star per parsec squared, so it's really very, very sparse. Therefore, ideal for making n-body simulation of that. Has a absolute magnitude of -5.1, so it's about 10,000 solar masses. Very extended, as I said, 20 to 30 which means parsec actually. It's 23 kiloparsecs from the sun and like 19 kiloparsecs from the galactic center, and it's high above the galactic disk. So in SDSS in the northern footprint, it's on the southern border of the footprint, but it's well above the bulge. And if we look at the mass function, for example, there's HSD data on the mass function in clusters, and it's very depleted in low mass stars. And these low mass stars are, this is maybe which hints where they are. So this is the surface brightness profile of the cluster. You see here, that's the part as you would expect it to be. You would expect surface brightness profile of the cluster to drop like that. Typical pink profile. But what you see is it levels off, and then you have this very shallow slope outside the tiny range, which is more or less here. I've shown the other surface brightness profile for 1851. The other project I was advertising. 1851 has an even shallower profile here, so it's almost constant. And if you look at Palmer 5, no matter how you model the cluster, you always get some orbit with an eccentricity of 4.5 or so. Orbited eccentricity of 4.5. So most likely NGC 1851 is on a very much more eccentric orbit, and close to its apocenter. That gives you this level, this shallow slope. So where does this come from? This comes from the debris of the cluster. So here is the cluster, and this is early data from SDSS, like the first, it was before the first data release actually. With Kupper et al. They looked into this, and they found this first part of the tidal stream, the stars floating out into the tidal place, very beautiful. Like in the last data release of SDSS, you can trace the cluster, the tails out to 22 degrees on the sky. Very long structure. It's like 10 kiloparsecs. So what else do we have in data? So there's also some thematic data. So the same team went to CAC and took some radio velocities here of stars where I thought there might be members of the tail, and the red ones, red dots are actually kind of confirmed cluster members. What you get is some sort of radio velocity gradient. So when we model the cluster and the debris, we also want to reproduce this velocity, the radio velocity gradient along like with longitude there. Kupper et al. In the same paper, they also tried that to model that with orbit fitting, as I said. And as you can see here, so they have 3 lines just going through all the data points there are. It looks like one line. It's how they generated this. And you get different gradients here in radial velocity. And what they inferred is that the halo must be very, very low mass so that you get a rotation velocity of 150 kilometers per second to match this radial velocity gradient. But we could have shown that just fitting in orbit is biased. So we need to model it more properly. That's what we're doing. So let me briefly explain the method, how to produce such a streak line. So assume you have your position of Palmer 5, you assume some distance, you have a radial velocity, you assume some proper motions. What you then do in a trial potential, you integrate it backwards for a given time, and then you start the simulation forward again, and while going forward, you release these test particles, and you integrate everything forward in time until the present day, and then you get a distribution of test particles, which you then can compare to your observations. This is a very schematic movie, but I like it. It's from Anna from Yale. running a paper on this right now. So assume these are observations, the red dots, and then this color line here are the test particles. As you can see here, the color coding here is it's like when the test particles have left their cluster. So you see here they are all overlapping the colors.
Can you explain how the streamline models are different from just doing orbit integrations with test particles that are released from the cluster's potential?
Sorry, I don't hear you acoustically.
Sorry. Can you explain how the streamline models are different from just doing orbit integrations of test particles that are released from the cluster potential and then are just moving in the post potential? Or is that?
You mean what people also do is like setting up a ball of stars and evolve it forward without self-gravity of the ball of stars, right? Mm-hmm. What you don't get in this is because you don't have self-gravity, you don't get an offset of the test particles from the cluster. Mm-hmm. So you would just spread the debris along the orbit of this ball of stars.
Right.
So, but what you need is this offset. Just imagine make the cluster much more massive, like Sagittarius massive. Yeah. Then the debris would have to have a huge offset from this initial group of stars, and you would not reproduce that.
Yeah.
So that's the difference here. So then you have a streamline model here. You have a streak line, and you have to compare it somewhat to the data. You need some likelihood function to spend some time to figure out how to compare its best. Okay, I'll talk about this in detail if you'd like. So Sarah has been working in the last year on this, trying to assess what we have for fun of it is the position of the sky, right? You can measure very accurately. We have a distance, which you can measure more or less accurately. We have a radial velocity, which is also measured to a very high certainty. But what we don't have is the Kupper motion. And what we of course don't know is the dark matter halo. So what we assume here is we have a spherical dark matter halo potential, and we just vary the Kupper motion and see for each pair of Kupper motion components, what do we get? What does the model look like, and what does our likelihood function return? So what you see is for two Kupper motion components, the log likelihood value. So dark blue is very good, and white would be completely wrong. And as you can see, we can rule out like large fractions of Kupper motion components, which you could also do by eye, because if the cluster, if the tails lie like this, then of course it's wrong. But what we find is like the best model here, if we run an n-body model with these Kupper motion components, we get a variable match to the SDSS data. It lies just on top of that. If we then take, as an example, this potential which was found for the Sagittarius stream, very simple exercise, just take the same triaxial potential and try to find the best fitting model in that potential. You see it has a very different Kupper motion here, and then if you run an n-body model for that, we kind of get the shape right, but what you see here in this blow-up, very nice blow-up by the way, you see it's totally off. So the stream is not really curved, like it has to be, like here. And it has a much lower likelihood value. Like the likelihood value, the log likelihood value is like 20 magnitudes lower as for the spherical halo. But we have more information, right? We have also the mathematic data. If you look at that, then it's much more clear. Here the radial velocity gradient just matches spot on, whereas in triaxial potential on this side, it's completely off. So we have to make an triaxial potential like the one suggested by Majesty. You have to make the cluster very, very fast so that it's closer to pericenter, that the whole system gets stretched and it just looks very straight. So you can kind of just rule out this triaxial and halo configuration for the one that Majesty suggested. But we can go further. We can put this machinery into MCMC from Daniel Forman, Mackie, and at NYU. and increase the parameters. So we can just leave all parameters free. It's 11 now. For example, like the halo shape, you can leave this completely free, and also like the geometry of the problem, like what's the distance to the cluster, what's the distance of the sun to the center. All these are free parameters. And what we get from that is now an attempt of comparing my results to other results. These are from different tracers. For example, Neden used globular clusters in a Milky Way to infer the mass of the galaxy. You get these huge degeneracies here between mass within a given radius and halo concentration, for example, halo. This is kind of the uncertainty we have to deal with. So it's an uncertainty, for example, for this black control line. It's an uncertainty of a factor of 2. So if I plot my results into that, they have very good agreement with all the other methods and have smaller error content. So what this means is that within a radius which contains, okay, what is M340? M340 is the mass within a radius at which the density of the dark matter halo drops to 340 times the critical density. Cosmologist, yeah. Which is more or less 100 kiloparsec. So the mass inside 100 kiloparsec is about 1.2, 1.3 times 10 to the 12 solar masses. For the flattening, minus slight. For the flattening, we get something close to spherical, maybe slightly oblate, and that's it. So not triangular at all. And that I conclude. Thank you very much.
Thank you very much, Andreas. Any questions that you touched upon yet?
Are the two streams symmetric?
Say again?
Are the two streams symmetric?
Symmetric?
Yeah.
No, not at all. That's very interesting.
Because I think it's not symmetric. Maybe it will affect the trajectory of the cluster.
Yeah. So the trailing tail of polymer 5 is much more dense than the leading tail, and what we think the reason for that is that the cluster is right now close to its apocenter, and it might have just passed its apocenter. And the densest part is the part which is still in apocenter. So what we see is there's apocenter and the cluster is already moving out of apocenter. So that's why you always expect this asymmetry.
Yeah, so I'm asking whether you have to consider the effects on the trajectory, because we have different amount mass on two streams that will affect the trajectory of the star cluster.
Oh, no. Mass-wise, it's the same. It's just that the leading debris is more stretched out because it's already falling into pericenter, whereas the trailing debris is being compressed. So, but no, the mass loss is symmetric. Yeah. The thing is, we don't see the polymer 5 is right at the edge of the footprint of SDSS. So from the leading tail, you only see 2 degrees or so, whereas from the trailing tail, you see 20 degrees. But that's up to it.
Both the Chinese stream and polymer 5, can you minimize them together to get the better results?
Yeah, of course, that's where it's all going.
This was just for polymer 5, I'm sure.
Yes. And here, with the student, I want to try to also model NTC 466, and then the next logical step would, of course, be combined. You can apply the same for Sagittarius. The Cambridge group has applied exactly the same methodology. So.
Somewhat related to that. Oh, sorry. I'm assuming you're not sensitive to anything that happens beyond the apocenter of the orbit, right?
No, not really. I mean, what we do is you assume some parameterization for the halo.
Yeah.
So what you can say is, if our dark matter halo has an FW shape, then of course, I mean, you're sensitive to scale radius and scale mass of the FW halo. And to explain the Palmer 5 result, you need a certain scale radius which actually lies outside the upper center.
Yes. I was quite surprised you're constrained on C, which is mainly scale radius and the outer radius, isn't it? And that's very small. Your error bar is pretty small there.
Right. Because you have to make this, I mean, once you fix the parameterization, then, I mean, no matter what constraint you get, 4.5, we don't know what the dark matter profile is beyond this radius, but if it's NFW, then this is the error bar you get.
But isn't C telling you more about what happens beyond the scale radius? Or is it also parameters or something like DNA?
It also has an effect on like inside the scale radius.
Did you use your streamline models to predict the orbits of the globular cluster, or predict the problem on things? If you, I used to probably have to assume a potential instead of solving for one, but.
Yeah, of course. I mean, you saw that in plot from Sarah's paper. Like field prediction, if we say, if someone else claims that the NFW halo is circle, then this would be the proper motion we should observe.
Okay.
Well, most likely. Of course, we could also put an error on that because it's basic.